Okay, so I've got one more problem for you before we wrap up atomic mass. We're not going to be completely done with this, but we will be done with just solving for the average atomic mass. And maybe it's natural abundances of different isotopes. So there is one question on your homework that asks you to find what the natural abundance for each isotope might be. And I have a feeling that a lot of you are going to be a little bit tripped up about that one because it's got a lot of algebra involved. So I decided to put one into the notes, that way that you guys will have something to be a guide for. So, if boron has two naturally occurring isotopes, so one is 10.103 AMU. The second is going to be 11.009 AMU. Okay? They may ask you, what is the natural abundance? Abundance for each isotope knowing that the average atomic mass is 10.811 AMU. Okay? So, that's a little difficult. It's a little bit difficult. So, we're not going to leave these things over percentages because I don't like to have X over anything. So we're going to make our percentages into decimals for this type of a problem. It's okay, all you gotta do is multiply it by 100 at the end and then you get your natural percentage, okay? Going back from decimal to not. So, I'm not gonna write this time my natural abundance. Why? I'm not gonna write my natural abundance either way, but I'm not gonna write my average atomic mass because I've already got it. That was something that was given to me in the problem. So it's gonna be 10.881. And then I'm going to write for my natural abundance X for the first isotope. I'm just going to name it X. You could be Y, Z, A, I don't really care. X is just kind of a common one that we like to use. Next is going to be, I'm going to write my isotope, or my atomic mass for my isotope. So that's going to be 10.013. And then I'm going to add my other one. So that's going to be 1 minus X. Well, what's 100? Guys, what's 100 in decimal form? So 100% decimal form is 1. So that's why we put 1 minus X times 11.009. And now it's just algebra. Okay? That looks really complicated, but it's really not that bad. The first thing you got to do with algebra, whenever you're solving an equation, is distribute. So we're going to distribute 10.88. So this should give me 10.013x plus 11.009 minus 11.009x. What's the next step in algebra? Combine like terms. So I'm going to combine my like terms, and I should get 10.811 is equal to -0.996x plus 11.009. And now I just move everything to one side. So I'm going to move my 11.009. Subtract out 11.009. And that should give me negative 0.198 is equals to negative 0.996x. Divide by negative 0.996. So my x should equal 0.19880, which if we put that into a percentage is 19.880%. Okay? So that's my first natural abundance. What do I do to find my second one? So that's my natural abundance for the first isotope, right? That's X. So I want to find 1 minus X. So what I'm going to do for that one is I'm going to substitute in. So I'm going to get my 1 minus X should equal 1 minus 0.19980. Which when I do that, it's going to equal 0.8012. And then I multiply it by 100 to get to 80.120%. Everybody understand? So this is how we are going to do. So that should be the most complicated atomic mass problem. Most of them are just going to be plug and chug. This is a little bit of algebra. I promise you it's not going to get any worse than that. And that's only going to be on your homework. That is not going to be on your quiz. So don't start panicking on me. Okay? So the next part that we're going to talk about. So we talked about this atomic mass. What does it actually do for us? Well, it tells us how much our molecule weighs, right? So if I have just an element, it's going to have an atomic mass. That's going to be its molecular mass. But what if I have a compound? What if I got sodium chloride? That's what's going to be able to be calculated, known as the molecular mass. Okay? So this is the mass in AMU of a molecule in a molecular compound. Okay? So, what if I asked you this simple question? What is the molecular mass of SO2? Stump you a little? So, the first thing I'm going to do with this is I'm going to look at my periodic table, because I didn't give you any AMUs or anything like that, so you're going to use your periodic table and it'll be fine. Okay? Didn't give you any isotopes, so you're just going to use your periodic table. And I'm going to find that my average atomic mass, so for S is going to equal, so for sulfur, is an equal 32.065 AMU. And my average atomic mass for oxygen is going to be 15.999 AMU. Okay? So now I look at my molecule. My molecule is SO2. How many sulfurs are in there? There's only one. Okay? So the first part is this per. So one molecule, one atom S is going to be in one molecule SO2. So per atom S, we are going to have 32.065 AMU. Okay? The next part. So how many molecules of oxygen are there? It's a little bit more tricky. There's 2. So per 2 atoms O go into for one molecule SO2. So, and I'm going to multiply that by one atom O has 15.999 AMU. Okay? So, multiply this all out, add it together. My atoms are going to go away. So I should get AMU per molecule of SO2. And that's what our units are essentially going to be. So my molecular mass for this will be 64.063 AMU per molecule SO2. Okay? It's literally just using things putting things correctly into your calculator. Once you've done that, this is the answer you should get. And that's what you're going to use later on to solve for when we go into stoichiometry. We'll explain a little bit more about that. Okay? So, think you can do that? Now we're going to make it even a little bit more difficult. So we're going to go from AMU and we're going to introduce this thing called a molar mass. Okay? So, and this is the mass of 1 mole of a substance. And this is expressed in grams per mole. Okay? So what's a mole? Right? You probably never heard of that, I mean, unless you're talking about the animal, but that's not what we're going to talk about in this class. So, a mole is an amount of substance that contains Avogadro's number of particles. So, and that's usually expressed in MOL, that's the shorten for it. Avogadro's number. And we're not going to talk too much about this, but we will talk about it when we get to stoichiometry. So I'm just kind of going to introduce it, and then we'll like hit home with it during that chapter. So that's going to be 6.022 times 10 to the 23rd. So that's Avogadro's number. It's atoms per mole. So it's going to be atoms per mole there. So the formal definition is the number of carbon atoms in exactly 12 grams of carbon-12 isotope. That's how he discovered it. So are you really concerned with all that definition? No. You are concerned with this number right here. 6.022 times 10 to the 23rd. It's probably memorized. I probably could say it in my sleep a million times. You should memorize that number, because I'm not going to give that one to you. So, how do we go from atomic mass to molecular mass to molar mass? Well, first I got to ask myself, what is the molar mass of an element, right? So I'm just going to pick one. And I'm going to go with gold. Because why not? Okay? So I'm going to start with my atomic mass. My average atomic mass that I can find on the periodic table is 196.97 AMU. So that's what I found on my periodic table. So I start by writing that. So I've got 196.97 AMU per one atom. Ooh, that's not how you spell atom. Per one atom AU. Okay? Now I am going to use the Avogadro's number here to make a point. You put it through your calculator, you may not get the exact answer I'm going to get, but it's going to be close enough. So, 6.022 times 10 to the 23rd atoms AU per 1 mole AU. Okay? Now 1 AMU, so 1 atomic mass unit, has the weight of essentially a proton and a neutron, which do have the same weight. So that's going to be 1.66054 times 10 to the negative 27 kilograms. Okay? So I've gotten rid of my atoms. AMU. Atoms. AMU. What is my molar mass written in? It's written in grams per mole, right? So I've got my mole on the bottom. I need my grams on the top. What do I have on the top? I have kilograms. So I need to multiply that whole thing by 1 kilogram per 1,000 grams. Okay? And that should give me, essentially cancel both of those numbers out. So this should be 196.97 grams per mole AU. So what does that mean? It means that my molar mass is the same thing as my atomic mass, because the conversions are very, very similar. So when I look at that number on the periodic table, I'm able to calculate my molar mass too. Not just my molecular mass, not just my atomic mass. I know that this is going to be my molar mass for gold. So if I have gold in a compound, I'm going to add that into it. So, what if I asked you, what is the molar mass of CO2? Well, do the same thing I did before. I'm going to first look up what my my molar mass for carbon is. And that's on my periodic table because it's the same as my atomic mass, right? So, see, it's going to be 12.011 grams per mole. And I'm going to look what my molar mass of oxygen is, which should be 15.999 grams per mole. Okay? So, if I wanted to find my molar mass of CO2, I first look, how many carbon molecules do I have? I got 1, right? So it's 1 mole of carbon per mole CO2. Okay? Times 12.011 grams per 1 mole C. So now I've got rid of this, gotten rid of this. That's done. Now I'm in grams per mole CO2. Plus, how many atoms do I have of oxygen? I've got 2. So it should be 2 moles O per mole CO2 times 15.999 grams per mole O. So, and when I add those together, I should get 44.010 grams per mole CO2. Everybody understand? So, we can take this one step further and apply it to determining mass, because does anything actually get weighed in moles? No. We weigh in grams. So we use moles to determine how we can get to a specific substance, right? But at the end of the day, we are weighing things out in grams. So what if I asked you, what is the mass of 0.462 moles HE? So I've got 0.462 moles HE, right? Times. Well, I'm going to put 1 mole HE, right? Because it's always something per mole. And if I looked on my periodic table, I would see that it would be 4.0026 grams HE. When I multiply that out, I'm going to get 1.85 grams HE. Okay? So, that was pretty simple, right? That was a pure element, so all we had to do was just look at our periodic table. That gave us our molar mass. However, sometimes we're going to have compounds. And we have to first do something else before we just determine that. So, what is the mass of 0.505 moles NaCl? Okay, well first, I determine the molar mass of NaCl. Okay, that's the first thing I gotta do whenever I look at these problems. I gotta figure out what my molar mass is. So if I do that, how many moles of Na are in NaCl? Only 1. So I write 1 mole Na per mole NaCl times, if you go and look on your periodic table and find where sodium is, which should be on the far left side, like 3rd row down, you would find that it's got a molar mass of 22.990 grams per mole Na. Okay, now we're in grams per mole NaCl. But we gotta account for that chlorine, right? So how many moles of chlorine are in NaCl? Only 1. So I'm gonna do 1 mole Cl per mole NaCl. And then if I go and look at my periodic table and I find chlorine, which should be on the closer to the far right, I'm going to get 35.453 grams per 1 mole Cl. And that should give me a molar mass of 58.443 grams per mole NaCl. So, what's the second step then? Well, I'm going to actually answer the question. So 2 will be determine mass. And so, if I do that, I'm going to first write what I was given initially, which was 0.505 moles NaCl times 1 mole NaCl per 58.443 grams. And that should give me 29.5 grams NaCl. Everybody understand how to do that? Okay. So, sometimes I'm gonna give you the mass, and I'm gonna want to know what the moles are. It's kind of important. It's how we convert things from one thing to another. So, I'm gonna ask, what is the moles of 5.00 grams of CaCO3? So calcium carbonate. So, first step I'm going to still do is determine molar mass. So that's my first step. So, I'm going to do, how many moles of calcium are there? There's only 1 mole. So I'm going to write 1 mole Ca per mole CaCO3 times. If you go and look in your periodic table, which you should have out, you will find that calcium has 40.078 grams per mole calcium. Okay? The next one, I'm going to add carbon. We already know what carbon is. We've done that enough times. How many carbon molecules are there? 1. So 1 mole carbon per mole CaCO3 times 12.011 grams per mole C. And one final thing, we got to look at oxygen. How many oxygen molecules do we have? We have 3. So I'm going to go and put 3 moles O per 1 per mole CaCO3 times 15.999 grams per mole O. Okay? So I add those all together, and what I'm going to get is an answer of 100.086 grams per mole CaCO3. Okay? My second step is going to be determine the moles. Right? So determine what I'm looking for. So this should be, so I start with my first information that was given, 5.00 grams CaCO3 times 100.86 grams per 1 mole. So we essentially flip it. CaCO3, CaCO3. So, and this should give me 0.0500 moles CaCO3. And that's about right because it's very close to 100. So just moving the decimal place over 2 will get the job done. So this is the answer. Everybody understand? So now I'm going to go ahead and try to upload these. We'll see how it goes. So let me know if you have any questions tomorrow. Hopefully everything will upload okay and we will be good to go.